Blindly copying nature's way of doing things wasn't always a good idea.
They had this interesting analogy that just like when you made planes, you didn't have to make them with flapping wings. The biology didn't make any difference. We just bypassed biology and evolution and made planes with motors, and we made rockets. And if we'd spent our time trying to make things that flap their wings like people did in the early days, we wouldn't have ever had anything that flies. So it doesn't matter at all how the brain makes intelligence. We don't have to model the brain any more than you have to make something that flaps its wings in order to make something that flies.
In the early 1960s, Hubert Dreyfus was a young philosopher working at MIT, one of the few representatives of the humanities in an institution which lives and breathes science. Students of his, who were immersed in the exciting new frontier of artificial intelligence, began trying to convince him that for philosophy, the writing was on the wall.
Students would come into my courses on Heidegger and Wittgenstein and say that you philosophers have had your 2,000 years and you haven't come up with much, but we are beginning to, in fact, we've already practically finished understanding perception and particularly intelligence, reasoning, and so forth. And in effect, the ball has passed to us. And I was amazed. I had heard nothing about that.
Can machines really think? Even the scientists argue that one.
I'm convinced that machines can and will think. I don't mean that machines will behave like men. I don't think for a very long time we're going to have a difficult problem distinguishing a man from a robot. And I don't think my daughter will ever marry a computer.
The MIT scientists wanted their computer mind to interact with the world. So they built a gripper for a hand and a TV camera for an eye. The task they set it, to stack blocks, was, on the face of it, child's play. But it turned out to be more difficult than anyone could have imagined.
It's easy enough to get a picture into a computer. The trouble is that a block or a box is different. You move it this way, it's a different shape. And so you almost never see the same thing twice. Sometimes there's shadows on it, sometimes it's darker or lighter. Different boxes have different surfaces. Sometimes there are things written on it. So that even though to you or me or a child, the idea of seeing a block seems simple, it's actually very, very complicated.
But the difficulty the program had in recognizing blocks was just the beginning.
For example, we asked the robot to build a tower of blocks. And guess what it did? It started with the top block, put it there in space and let it go, because the machine didn't know that if you let go of something, it will fall. It didn't know about gravity, and it didn't know about the kinds of things that every 2-year-old child knows. So it took several years to do that.
On this side of the Atlantic, things weren't going any faster. At the University of Edinburgh, another ambitious vision project was underway. This documentary from 1971 showed just how intractable some of the problems were.
Freddy is a computer, and his world consists only of this round board and the objects on it. We immediately see this as a cup. Now the computer tries.
After the first phase of processing, we have something which looks like this. The computer has sorted out the 4 major regions. Top of the cup, body of the cup, hole in the handle, and this irregular region, which is the shadow.
After painstakingly working out where the object ends and the background begins, the computer is ready to name what it's looking at.
On the teletype, you can see the results coming out.
But it took 10 minutes. A 2-year-old child would recognize it immediately.
The problems of moving and seeing at the same time were even more taxing. At Stanford in the early 70s, Hans Moravec bravely tried to get his cart, a trolley connected to a massive computing engine, to cross a space, avoiding objects in its path. Each flash represented 15 minutes of thinking time, which tied up the department's computers.
A 4-year-old is already equipped with wonderful circuitry to look at the world and detect the presence of objects and to note the imminent collisions and to avoid them. So a 4-year-old can toddle across a room with apparent effortlessness. The Stanford cart used a hierarchy of programs which were anything but effortless.
The computational problems of vision were so immense that many AI people decided to avoid the area and concentrate instead on a purer form of intelligence, a truly disembodied mind, one that didn't need eyes, legs or hands.